Yeah, thanks for having me here. It's a great honor to speak on this conference. What I would like to talk about today is joint work with Julius de Günther and our supervisor Udo Seifert. And it's about relaxing the Markov assumption for thermodynamic inference, something we have called Markovian events. So to give you a broad overview over the topic, although most of you know, many of the models we describe in stochastic thermodynamics are inspired by something like, say, protein folding, as the one you see here in the Stiegler experiment, or come from something like molecular machines, as you might see here. The paradigmatic model class we describe this with is Markov networks. You see the network structure, and they are Markov if a particular state in this network describes the system completely. This is our underlying assumption. And if you take this for granted, then you have the typical variables you're familiar with. You describe the probability of this to be in some state I, pi of t. The dwell times in this kind of state are then exponentially distributed. You have an escape rate gamma I. You have transition rates kij from state I to j. And these give rise to transition probabilities p from I to j. These are the probabilities that, given you're in state I, the next one will be j. This kind of dynamics can also be equivalently described by a path weight. And this path weight gives you the probability to draw an entire trajectory gamma of t as a whole object going from time 0 to time t. And this path weight is already characterized by the Markov property as defined here, which means that the future time evolution at times greater than some value tau only depends on the past through the time tau and the actual present, the state where you are at time tau. So the future only depends on the past via the present. That's the Markov assumption here. So these systems in our thermodynamic context are then equipped with a physical notion of entropy production. And we know how to decompose this one into stochastic and medium contributions on the level of individual trajectories. So what I mean by that is, first, you have a stochastic contribution to your entropy, which is just the negative log of the state you are currently in. And both the stochastic and the medium entropy production change when you make a transition from I to j. And it's just the log ratio of pi kij over the reverse rate of the transition. From this fluctuating quantity, you can then calculate the mean entropy production rate, which is this quantity here, which you're probably kind of familiar with. And at a first glance, you can only calculate this mean entropy production rate if all the residence probabilities in the steady state, for example, and the transition rates kij are known. So if we now consider the case of a coarse-grained network, similar to what you've seen before in Christian's talk, for example, in a coarse-grained network, you assume that not everything is accessible. You do not have access to this fundamental level where you have all these kind of states. So, for example, this middle Markov network here, where you can't discern state 1 and state 4, and can only see whether you're in the hidden state H. In this case, you cannot directly calculate the entropy production rate. And in some cases, you might even ask the question whether there actually is an underlying Markov network you, in some sense, can even approximate with your description. In all these cases, to recover thermodynamic quantities, you would need some inference, some schemes to actually get back to that. And that's the big question, what I'm talking about here, about these red arrows, how the coarse-grained description allows you to recover thermodynamic quantities like the mean entropy production rate, or more detailed information about, say, the topology or driving affinities, something like that. And this inference is thermodynamic in a double sense. First, we make use of thermodynamic consistency conditions because this is a physical entropy production. So we have something like local detailed balance at our hands. And second, we are interested in thermodynamic quantities of which we know what they should resemble and model. So with this big picture settled, my outline will be the following. First, many of the results in this very active field of research are of the following form. They are mean entropy production rate is greater than or equal to some kind of quantity x, which we interpret as a mean entropy production estimator. And of course, to be better than the second law, x should be greater than or equal to 0. And of course, now in the field, there are many results you can apply this to. For example, the TUR, for the TUR, you plug something in like the precision of a current. You can use some correlation effects, transports, coherence phenomena. And all of these give you a single bound on the mean entropy production rate in some sense. You could, in principle, also adopt a second approach. Namely, if you look at the coarse-grained model, it still shows some kind of dynamics, which of course contains less information, but it is still some sense of dynamics. So you could ask yourselves whether you could also keep the fluctuating notion of entropy production of delta small s and have a random variable on the coarse-grained level, which is defined in terms of the coarse-grained trajectory. In this case, we have different questions arise, like how to define a coarse-grained entropy production that is actually fluctuating, when is it meaningful, and what properties would be like. As an illustration here, if we say that the blue trajectory is some kind of microscopic motion, microscopic dynamics in a sense, and the red one is coarser, these dashed lines here illustrate this kind of bound between the mean values, whereas the fluctuating quantity would contain more information than that, but less than the microscopic trajectory. It's a kind of intermediate feature. So I will first show you something about this first approach, and then after that, I will come to this second fundamentally different thing. So first of all, I would like to start with a small Gedanken experiment, namely a very simple three-state network, of which we know that if we just observe a single Markov state, then we cannot discern equilibrium from non-equilibrium in the steady state. This has been pointed out in this work here, for example. But now my claim is that in the generic case, almost any kind of additional information that you may get here is helpful and will allow you to actually discern non-equilibrium from equilibrium. To have an example here, we assume that we can observe undirected transitions G between state 2 and state 3. So why do I choose undirected transitions? Because if you have directed transitions, the problem is already solved. You can just see whether net going downwards is more or less than net going upwards. So you see whether you have a current. But in the case of an undirected transition, you have two symmetric symbols, 1 and G, which also look like 1 and G under time reversal. So at first glance, you might think that, given some kind of Markov model like this one, be it justified or not, cannot feature a sustained current, so you might not discern the steady state. But one can actually do better than that. Looking at it in a bit more detail, one can have a look at the waiting time distributions, T1 and T2, during the times where you are not in state 1. And in the generic case, where one of these transitions, 1, 2, or 1, 3, is faster than the other one, you would, on average, see some effect like this. Let's assume the transitions between 1 and 2 are faster, then the symbol G would appear after a shorter time. After a shorter time, you have transitions 1G, then you would see these G1 transitions here. These would take longer on average. In such a case, if you take the backward trajectory, the G's would appear rather at the end between the two 1 symbols and not at the beginning. So on some kind of generic trajectory, of course, this would not happen every time. So given what I've illustrated just now, this is just some kind of heuristic picture. If we want to formalize it, then we'd have to think about what kind of in what sense are these waiting time distributions independent of each other? How can we break the long trajectory apart into smaller independent subunits? And for this, what we can use is that the state 1 is actually a Markov state, which means that the waiting time distribution, which gives us T1 and T2 here, is independent from the one T1, T2, T3 here. So calling these these small fragments of trajectories snippets, which always have to form 1, a couple of G's, and a 1, we see that the Markov property, which holds whenever you in state 1, gives you statistically independent waiting time distributions for these creatures here. And given these distributions, you can write down an entropy estimator, which looks roughly similar to what you expect from a Kolbe-Gleibler divergence, namely a sum over the probability to see the forward thing times the logarithm of the probability to see the forward snippet divided by the probability to see the backward thing, which in hindsight is not too surprising, but this is just a quantitative statement of the fact that you can still discern non-equilibrium in this kind of setup. So going to the more abstract result from this minimal example, oh no, sorry, one more thing first. Let me first illustrate this example more quantitatively with some numerics. So we have just seen that if the transitions 1 and 2 and 1, 3 here have different speed, we would generically observe a better quality of our estimator. So quantifying this asymmetry between these two links through some parameter s, which is only 0 if you have an exact symmetry under flipping of state 2 and state 3, we can see that our estimator is always of order 1. You see the quality factor on this plot, which is not logarithmic, is between 0 and 1, with some kind of average maybe around 0.3. And this only takes the statistics of waiting time distributions into account, which have 2 time arguments. So we only take psi of t1, t2. If we go up to orders of 4 arguments, we have additional improvements again of the order 1. For example, this black dot and gets improved to this black cross here. So after this numerical illustration, let me now turn to the general abstract result. As long as you can cut your trajectory apart into small fragments, into these snippets, via these Markovian events here, we can have an analogous result for the entropy estimator as the one depicted earlier. Again, a logarithm of a forward pathway divided by the backward pathway in some kind of Kullback-Leibler divergence form. The interesting thing here is that we are able to formalize the property, what we actually need to cut apart the snippets. It is a Markovian event property, which in contrast to a Markov network only holds at certain points or times in our trajectory, at particular events. And going from one Markovian event to the next one, we can even include non-Markov information in our snippets, like the symbol G we did before. And in this sense, this is a dynamical unit which we can plug in here into this entropy estimator. So this concludes the first half of my talk. But let us now turn to the second question, giving you a rough comparison between what Markovian events can do for you and what you actually have if you have full access to the underlying Markov network. You see that in the Markov network, you have an averaged entropy production rate, and you also have a fluctuating quantity. And of course, the second one is more powerful than the first. Like an average over this one gives you that one. Now we already have the averaged result. So a natural next question is whether we can fill in this blank here, even if the Markov property only holds at certain points in time, and if we have a coarse-grained system here. And the answer is you can. And now the question is, what's the conditions and what's the properties you would like to have? So some properties an actual fluctuating coarse-grained entropy production should have is, of course, to only use coarse-grained data. And now the second one is something a fluctuating entropy production should have in contrast to just an estimator, namely some kind of additivity property here. If you have a coarse-grained trajectory gamma 2 after a coarse-grained trajectory gamma 1, you would like the entropy production to be additive in such a sense. And the third property is inspired by the sigma hat smaller than or equal to sigma estimator. So just the property that your estimator underestimates the entropy production. This one we would like to keep, but now resolved for for every individual coarse-grained trajectory gamma. So these three properties are satisfied if we define the coarse-grained fluctuating entropy production in such a way, which might be not too surprising in hindsight, but note that here below we don't have a tilde above the J. If you had one here, you wouldn't have the additivity. So this J without the tilde here is a bit reminiscent of underdamped Langevin dynamics. But now, just to point out a technical detail, we need a slightly refined definition for Markovian events. The future is independent from the past property now has to hold on the microscopic level, not just at the coarse-grained level. This is just a technical detail. Given that you now have a fluctuating entropy production on the coarse-grained level, you can now think about what is all the benefits of that? What can we do with that? And 3 of the questions you can actually answer through such a quantity beyond an estimator on the mean entropy production is: when does entropy production take place? Where does entropy production take place? And how much do particular classes of coarse-grained trajectories contribute to this kind of coarse-grained entropy production? To give some kind of explicit example, let's consider this 6-state Markov network, and let's assume we can observe 2 pairs of transitions and their reverse here. Then we can, in principle, write down some kind of table, which resolves the first event of some kind of snippet and the final event of some kind of snippet. So what we could resolve is trajectory snippets of the form, what does K to K contribute in contrast to, let's say, L to L tilde? And of course, this table contains a large number of estimates. So each of these numbers on the right-hand side is a lower bound on the corresponding number on the left. And if you add all of these contributions together, you get back that the mean entropy production rate is bounded by the corresponding estimator. And what you can also do is you're not limited to the steady state, actually. So to give an experimentally relevant example, let's have a look at a protein unfolding experiment, in particular the one done by Stiegler and co-workers here in this work, which is modeled as a 6-state Markov network. They have identified the underlying network in this case. So if we take this network as our basis and apply time-dependent driving in the sense that we model pulling apart the protein by optical tweezers and modify our transition rates accordingly, then what we can actually resolve is the entropy production which this model gives you for a unfolding event if you start with the optical tweezers very close and pull them apart. And we even retain this kind of information if we assume that all the intermediates of the protein are indistinguishable. So in Stiegler's case, in that experiment, they could actually distinguish these kind of states. But the crucial thing here is, even if you can't do that in some kind of generic case for other proteins, we still maintain this kind of information. So here you see some kind of plot for different unfolding experiments from a different starting force to a final force, these simulations here. And what we have compared is the microscopic entropy production, which we get from the underlying microscopic picture from the 6-state Markov network, and compare them to the coarse graining, which we imagine when we can only see the unfolded and the folded state. And as you see, we not just get a qualitative quantifier of non-equilibrium, we even reproduce the nature of the curves here, and we get estimators of up to 100%, but on average something like 90% estimators. So I hope I have convinced you that there is still much that can be done here. But now I would like to turn the eye to some technical details. Comparing again the Markovian event formalism I have introduced with access to the underlying Markov network, I would like to point out that if you have a coarse-grained setup where you don't see the underlying Markov network, then actually assuming the Markov network includes assumptions on the part of the system you cannot assume. So not only do you make assumptions that cannot be verified, it also has, as demonstrated in this work, for example, limited applicability in practice. You make some more assumptions than you would actually need. And in contrast, this Markovian event formalism, which only imposes the Markov property at events you can actually observe, does not make this kind of Markov assumption on the underlying part, on the unobserved part. So you could also falsify the Markov property based on given data. For example, consider this four-state Markov network here. If we lump these two states together into a state H, and not treat the Markov state 4 or 3 as our Markov events, but the lumped state H, our entropy estimator might actually overestimate the entropy production rate. So we get inconsistent results. And not only would this give inconsistent results, we could also actually check that H is not our Markov state. For example, based on a checking its waiting time distribution, whether it's exponential, or on a more general criterion, which I have no time to go into detail here, or following a more constructive approach, if you can justify that there's a local timescale separation, for example, that 1 and 2 are fast, of course you can also get Markovian events from that. All right. So after this discussion, let me summarize the results we actually have here. We have a versatile framework for an entropy estimator for an estimator of entropy production that can be applied to various systems, and we have also discussed the conditions under which you have a entropy production as a fluctuating quantity on the coarse-grained level. This allows us to localize where entropy production actually happens. There's some more results which I did not have time to go into detail. For example, you could also apply the snippet formalism, the technique of cutting the trajectory into small independent parts to get estimators on the affinity. But you would have to check our work for that. And of course, there's also more questions that could be addressed from here. You have also, in Christian's talk, seen a different approach before. You also know the TUR. These are all different methods to estimate the entropy production rate. And of course, now the question is pending which one performs good in which setup, and what to do in more general model classes, like what if you have odd variables or memory effects. But this is all stuff for future work. And for now, I'd like to thank you for your attention and would be happy to take your questions on this work here.